Hope you enjoyed the first half of the webinar. The second half of the webinar, Jeffrey Kotcher will talk more about the architect that goes into tiered adaptive storage. Hope you enjoy.
So now Jeff's going to talk a little bit about how we can use TAS for HDFS and to support these analytics use cases and workloads. So with that, I'm going to let Jeff talk a little bit about this, and I'll advance the slides for you, Jeff.
Okay, great. So I'm Jeff Katcher. I'm a storage architect for Cray, working in our business development group. And what I'd like to talk about is the use of TAS to support and improve analytics workflows. These days, when people think of analytics, what they really think of mostly is the Hadoop and the Spark sort of foundational ways of doing things, and that's all based on MapReduce. And I'll talk a little bit about Hadoop here, what it is for people who aren't familiar with it. So when people talk about Hadoop and Spark, which is a more sophisticated version, but philosophically is quite similar, takes arbitrarily large data sets, splits them across nodes in a cluster, does a certain amount of processing on each node in place with the data stored on the nodes, then collects the results and assembles it and returns it to the user itself. These systems actually evolved from systems used by the likes of Yahoo for doing the log processing, where they would have hundreds of web servers, each web server running its logging processes, but they were running into problems where copying all of the logs back to a central place and doing analytics on them was becoming unwieldy. So they improvised a system where they could actually request the web servers themselves to do certain classes of analytics on the web server itself and then merely bring the results back. And these systems have evolved from being into relatively improvised web systems, a relatively simple data into being enterprise support systems. And there have been scaling issues as well. As you can see on the diagram, this sort of zooms into the previous diagram, showing that the data for each Hadoop data set is actually split into pieces and distributed amongst the sets of the cluster. And the sort of file system that's used by Hadoop is called HDFS, or Hadoop Distributed File System. And HDFS is sort of a meta file system, meaning that it's actually an aggregate of real base file systems running on systems themselves. And as such, it can be expanded and it can be aggregated from different types of file systems. So each chunk, by the way, is usually replicated about 3 times across the nodes. So what happens is that everything gets split into chunks, chunks get replicated, and then replicated chunks get spread across the cluster itself. When processing takes place, the system knows which data lives on which nodes and tends to place the computations on those nodes so that data doesn't have to flow across the network itself. One of the things that's been recently introduced, relatively recently introduced to Hadoop is the idea of tiering. It used to be that HDFS was a monolithic structure. You just saw it as one thing. It was comprised of multiple pieces, but the multiple pieces all acted as one. But it became evident that with the evolution of storage technology and how things are splitting into spinning disks and SSDs and archive systems and RAM disks, that HDFS itself had to be made more intelligent. So data types and storage types have been added to Hadoop with actually Hadoop version 2.3, and we're currently on Hadoop 2.7. And so all of this is actually in standard Hadoop distributions. So when you create an HDFS file system, you create it out of pieces, and there might be a disk piece, there might be an archive piece, there might be an SSD piece. And correspondingly, HDFS data sets, directories, and files themselves can be tagged with arbitrary storage policies, hot, warm, or cold. And then there's a utility that is now included with Hadoop, with HDFS, called Mover. And when you run Mover, and this is a manual process to invoke it, the system will then transparently rebalance the system so that if something is marked hot, but it is not on disk or SSD, it will be transparently moved there. Things that are inactive but are currently living on hot disk, for example, will be transparently moved onto, say, an archive volume. And archive volumes can be set, for example, to replicate less or replicate more so that you can actually balance things to the uses that you want. And this is actually a system that's used in production right now by the likes of eBay. Because as we've moved into enterprise Hadoop, I mean, it used to be that a group owned a Hadoop cluster and all the data was there and all the data that was on there was more or less active. But, you know, in the enterprise, we've moved to larger and larger aggregates of Hadoop clusters where the total aggregate of the data in the cluster is far more than anything actually being used at any given time. So some group might be doing an analysis, and then some other group might be doing an analysis. And, you know, you let this build and build and build for a while, and pretty soon you have a petabyte of active disk. And not only do you have a petabyte of active disk, you have a petabyte of active disk distributed amongst, you know, 200 servers, 300 servers. And as Jason alluded to, the management exercise of that is very complicated. Not only that, it's expensive as well. But, you know, we have a solution for that. And, you know, the solution for that is TAS. And you can think of TAS as being sort of a magic file system where when things are copied to the file system, TAS keeps track of whether it's active or not and moves it either to disk cache for fast access or off to automated tape library and back for secure, cost-effective storage. And the thing about it is, since TAS appears as merely a file system, even though it has all of this workings, magic behind it to make it work, HDFS allows it to be aggregated into the HDFS whole. So you can see by this diagram here, you can actually take an existing HDFS system that's comprised of, you know, multiple disks on multiple servers, existing disks on existing servers, and merely map in, you know, one more volume into that HDFS assemblage. Only that one volume lives on TAS and is exported from TAS. But the system itself merely sees that part of the HDFS volume is disk and part of it is archive. So that if you have a directory, all you have to do is simply mark that directory as archive, and HDFS will integrate in and just automatically pull things onto the archive as required, or pull things off the archive as required, so that the amount of active space, the amount of active disk that you have to manage in your Hadoop cluster is greatly reduced. So you might be able to get away with, you know, 100 terabytes of disk versus a petabyte of disk, and let the system itself do all the management in the background. I mean, the tiering is there for Hadoop, but, you know, that's manual tiering, but you can offload things to not only an inexpensive system, but an inexpensive system or a cost-effective system that is automatic. Just so summing everything up is that only active data sets require a fast, expensive disk. So your Hadoop nodes can be configured with less disk, and, you know, possibly even faster disk as well, because it becomes more cost-effective to do that. You know, the use is very, very simple to use this model. You know, once the system is mapped in, you know, it's just simply editing a text file to tell your HDFS system that there's another component into the system, and the system, and then it just is automatically taken advantage of by the system itself. And lastly, you know, archive data is officially protected on long-term stable tape media. And you can't necessarily be assured that your valuable logs are being preserved properly on something like, you know, an arbitrary Linux file system sitting on, you know, cheap SATA disks, which is sort of the norm. But in fact, you know, things, enterprise-ready archival solutions, you know, like the currently available tape systems, you know, they multiply checks on the data. They have a lot higher degree of reliability over time because, in fact, they are made to last forever. I mean, oil companies, for example, depend on the likes of HSM systems, where they have things that are sitting in, you know, salt mines for 20 years, 30 years, 40 years, where, you know, the people who recorded them aren't even alive anymore, but yet they can still bring them back safely. And this is the same degree of reliability that you are now imparting to your data.
So, Jeff, now we're going to talk a little bit about the case studies. That's really, you know, it's amazing how simple it is to use TAS. And just to give people a sense of what our customers are doing with our products, I'm going to give you a few different use cases. One is an oil and gas use case where the customer Petrobras had a pretty large-scale Linux cluster they were using for reverse time migration seismic processing. And they had a number of NAS systems and GPFS systems deployed to support that, but they were finding some performance bottlenecks in scaling to the need that they wanted to go to. So with with help from Cray, they were able to go to Synexion and effectively scale out their scratch space cost effectively, and then free up the NAS and GPFS for the home file systems. So really, Synexion was just perfect in terms of pure scalability for performance for this type of workload. And then another example is what we've done over at KAUST, the King Abdullah University of Science and Technology, where they needed a complete next generation upgrade to their supercomputing facility. They came to Cray, and what Cray has delivered is a comprehensive solution that includes compute, data warp, Synexion for primary luster storage, and TAS as an archive system. The TAS archive, is starting at 20 petabytes with its current iteration scaled seamlessly to 100 petabytes. And this really gives them end-to-end data management like we talked about earlier, where the data can very easily get to and from the compute environment on down to Deep Tape Archive and back. And one of the real interesting recent things we've seen is just the performance numbers they've achieved with the flash tier and SSD storage is just remarkable. And again, this is a seamless solution end-to-end from high performance to Deep Tape Archive. And then one of what we call a next generation capability system is at Los Alamos National Labs. It's a project that we refer to internally as Trinity. And this is just an example of a large-scale solution that includes both Cray compute and storage, where we're delivering, unprecedented performance numbers in SSD, and the underlying Synexion file systems themselves are going to be quite massive in terms of 40 or 41 usable petabytes each in one file system. So this is really an incredible deployment that's underway now. And again, the burst buffer capability is really important here because when Los Alamos runs a job in compute, that job could be going for months. So if you, for example, have a job that's running 6 or 7 months long and something on that job crashes and it needs to restart, a key thing they needed to do was be able to quickly restart that job from where it left off. And that's what a key thing that data warp is going to help them with.
Well, thank you for watching our webcast today on storage. If you have any questions for Jason or Jeff, feel free to reach out to me. My name is Todd Quinn, and my email is tquinn, TQUINN, @cray.com. Thank you for taking the time to watch our webcast.